Stanford University.
Welcome to EE380 Fall Quarter 2010-2011. I hope that the students in the audience are keeping up with the coursework. As I often say, if you try and do it all in the last week, you usually won't make it. Something comes up. As I've also said before, there are advantages to being live. In particular, there's almost always something that happens really interesting after the cameras go off. Last week was a good example. Someone in the audience showed camouflage test sites on Google Earth, where you can actually see people trying to experiment with camouflage on a very large scale. Okay. Next week's talk is by Emmanuel Candes on compressive sensing, which appears to be a very big thing. Sensors also being how we deal with the world in computers. We regularly have talks in 380 on programming languages, because programming languages are perhaps the fundamental invention of the digital age. And at Stanford, we teach that there are principles of programming languages and there are fundamental issues. And at each point in time, or each point in application, the different weight between hardware matters, the hardware capabilities we have, how people work, and the types of things we're trying to build have changed. So our tools have changed. Our programming languages have changed. That's why we keep coming back to programming languages. Today's talk reviews that history and looks at what has worked in the past, what didn't quite work, and discusses where we might go in the future. Doug Crockford of Yahoo. Yay! So
I'm going to start with a regretful announcement. Today's talk is going to be about JavaScript. For the next hour, I'm going to be talking about JavaScript. And I would not be offended if you were to walk out right now with that knowledge. But I recommend that you stick around because I think I can make it worth your while. JavaScript, while being the world's most misunderstood language, has also sort of surprisingly become the world's most popular programming language. There are more people writing in JavaScript today than any other language. And you could well argue that most of those people should not be programming in any language, and I wouldn't argue with you. But in fact, that's where the most people who are programming are doing it. There are more JavaScript processors running on more computers than any other language processor. It's the language of the browser. It's now in operating systems, it's in your best databases, it's in embedded applications, it's even finding its way into television sets and telephones. So because of that ubiquity, JavaScript has become an interesting language. At the same time, it's the world's least popular language, in that if you were to take a survey of any group of programmers and ask what language do you hate, by far the most common answer is going to be JavaScript. And that will include most of the people who are programming in JavaScript, which is quite different than the communities of other languages. I'm also going to be talking about loops and how loops interact with JavaScript in a number of ways. So JavaScript is an odd amalgam of features from some other languages. It gets its syntax from Java, and so that's why it's familiar looking, even though it doesn't behave the way you might expect it to. It gets its functions from Scheme. In JavaScript, functions are first class, lexically scoped. It's got closures. It does that stuff right. A lot of people are surprised to learn that JavaScript got anything right, but in fact, it got this. In fact, it's the first Lambda language to go mainstream. JavaScript is sort of leading the way in bringing functions to the masses, which is a wonderful thing. JavaScript was also influenced by Self, which was David Unger and Randy Smith's Smalltalk derivative that was developed at Park and then at Sun Labs. Self simplified and amplified the JavaScript or the Smalltalk model by eliminating classes, and so that objects are just the fundamental thing of which everything is composed. And that turns out to be an amazingly expressive idea, and JavaScript implements that in a really nice way. So let's talk about loops. So here's a loop statement, and it says loop, and there's a block, and as you would expect, you can put some statements inside that block, and they'll repeat over and over again until something disrupts that. JavaScript doesn't actually have a loop statement, and I think that's a shame for a couple of reasons. One is that it does have loops, and we'll get to them in a moment, which can exit at the top or exit at the bottom. But I find that most of the loops I write seem to exit out of the middle. I don't know if it's just me or just what, but the others don't match the way I think. And I can write a loop that exits from the middle by doing while true or for nothing, but that looks silly. And I'd like to be able to do the more primitive thing, because that's actually what I'm trying to express. But the other is that if we could have a smaller core language and then have simple sugar amplifications of it to make it more expressive, then that smaller language would be easier to reason about. And as we think about the security of the web and the security of JavaScript, that turns out to be an important consideration. So if we had a while statement, then we could see how we could transform, or if we had a loop statement, we could see how we could transform a while statement. Simply take the condition, reverse it, put it in an if and a break. And then having this, we can understand what a do statement does. But the do statement looks quite different than the while, but as we can see what it actually is composed of, it's just the same thing with the exit at the bottom. Then we have the for statement, which I found is very confusing to students who are new to programming, because you've got three clauses and it's not obvious to a beginner what each of those clauses represents. It's a very vague construct, but if you see what it actually generates, then it's pretty clear what the thing is about. Another way you could think about loops is using recursion. So here I'm going to take a while statement and replace it with a function which will call itself. And that will have the same effect with two conditions. One is that it turns out in JavaScript you can't take any block and turn it into a statement body or a function body, because there are some things like the this pseudoparameter and the argument pseudoparameter whose meaning changes when they're nested inside of another function. And there's some statements like return and break, which also change their behavior when they're inside of another function. The other condition is that JavaScript does not do tail recursion. It does not do proper tail calls, does not optimize this pattern where you've got a return of the invocation of a function. In some languages, this call and a return gets replaced with a jump. And that's a very nice mechanism for writing loops. And JavaScript doesn't do that. So this will be more expensive than the equivalent loop. I hope someday we fix that in JavaScript, but that's a long way off. But that's not what I'm here to talk about. What I'm here to talk about are event loops. And in particular, in the browser, which is where JavaScript is the most important, everything is built on the event loop. So the browser keeps an event loop which contains callback functions, and the triggering of those callback functions can come from either the timer or from I/O events such as clicking or typing, or from the network. From when something is received, then we can get a load event. Then each of those event handlers is executed as one turn. It will run to completion and will not be interrupted. So it has complete control of the JavaScript engine until it completes. So the prime directive when you're in an event-driven system is you must never block, you must never wait, you must finish fast. That's an unnatural way of thinking about programming for some people, but it's very natural for people who are programming in the web. So there are a lot of things which are awful about the web API and the way that browsers work, but this is one of the good parts. This is one of the things that JavaScript and the browser got right, is this event loop-driven model. But because it's the browser, it didn't get everything right. There are some blocking functions which are available, such as alert and confirm prompt, which will block the main event loop, the main browser thread, so everything stops until the user dismisses that. So it's an appropriate thing to use when debugging, but generally in applications you want to avoid those. Also, there's an XML HTTP request, which is a mechanism in the browser for making a data link to a server. and it provides two modes of connections, blocking and non-blocking. I think that was a mistake. Only the non-blocking form should be used. So does everybody know who this nice lady is? Yeah, it's Grace Hopper. Everybody should know Grace Hopper. This is an amazing lady. And it sometimes alarms me that people in this profession do not know their own history. She's an important lady. She was the first woman at Yale to get a PhD in mathematics. The second? I just read a biography that said she was first.
I just published a review. I noted the other one.
The second woman at Yale to obtain a PhD in mathematics. She then went on to Vassar, where she was on the faculty teaching mathematics. When World War II broke out, her husband enlisted, as did her brother, as did a number of cousins. So in 1943, she did too. So she gave up her tenured position to join the Navy. Being a mathematician, she thought she might be doing cryptography or code breaking or something with numbers. Instead, she was assigned to Commander Howard Aiken at Harvard and made to work on the Mark I, which was, I don't know if we would consider it a computer today, but it's very, very close. It's one of the precursors of computers, certainly, an automatic calculator. So when she got there, she was told to figure out how the machine worked. So she basically had to pull it apart and figure out what it did. And then she was told to write a manual. So she wrote the first software manual, the first programmer's manual about how to program this strange machine, which she did successfully and then trained a staff to program. And so they used the Mark I to develop numbers throughout the war, numbers in the design of ships and weapons and other things. It turned out to be a very useful device. When the war was over, she went to work for a company that manufactured the first mass-produced computer, the UNIVAC. This is her at the UNIVAC 1 some years later. At the time, and for a large number of years, computers were extremely expensive things. And they required a lot of ingenuity in order to program them. But humans were so much cheaper than machines that it was considered not a problem, that it's not significant. The hardware costs overwhelm the software development costs. Grace thought differently. She saw that the machines were so difficult to program and that finding people with the skills to do that was so difficult that they needed to find some better way of developing software. So instead of coding the machines using numeric codes, that they needed to express programs in a more useful way. So she developed a program called A0. One indication of how good a programmer she was that she didn't call it A1. And this was the first compiler. We call compilers because of A0. Her idea was to compile to create a program would be a specification which would describe a sequence of subroutines. And each of those subroutines would have a call number, like a book in a library. And they would be assembled from a library tape and put together to create a program which could then run and which could then be put back into the library for further use. So when we talk about calling a subroutine today or calling a function, I know when I first heard the term, it didn't make sense to me because it's not like making a phone call. It's completely not like that at all. It was because she was calling for a book from the reference library. Each subroutine had a call number, like all the trig functions started with T, so they looked a little bit like Library of Congress numbers. There were two styles of subroutines at the time. There were open subroutines, which today we would call an include. You just take the whole thing and stick it in memory. And then there were closed subroutines in which you could have a single occurrence and call it from several locations with the program and then return afterwards. In modern terms, A0 looked much more like a linker. It didn't have programming statements that we would recognize today as being a programming language. Eventually, the linker functionality got peeled off and became a different program, but the compiler name stayed with the thing that transforms programs. It went through a number of iterations. She gave it to her staff for further refinement. They came up with another language called A1, and then another one called A2. And through each of these iterations, they're learning more and more about programming. A2 was the first open source project. A2 was shared with all of the customers of UNIVAC, and those customers were able to use the program, were able to modify the program to make suggestions for its improvement, which got fed back to UNIVAC. So the idea of open source programming is not as old as computers, but it almost is. It had to wait for computers that had lots of instances that were the same in order to become open source. Prior to UNIVAC, every computer was a one-off, a research project, and after its completion, the next computer would be different, an improvement. A2 led to A3, which led to AT3, which was later renamed Mathematic. And we would recognize that today as a programming language. It looks very familiar. At the same time, IBM was going through a similar progression, and they came up with Fortran about at the same time. And Fortran is the one that's best remembered, but it was very similar in many ways to AT3. It was a huge advance in the productivity of programmers, and it was rejected by some of the best programmers of the day. They complained that programming took too much creativity and dexterity, that couldn't be replaced by the machine that they were trying to program. It turns out this is a recurring theme that we see over and over in the history of software, that the people who should be the first to recognize the value of innovation are very often the last. So one of the things that we saw in both AT3 and in Fortran was symmetrical read-write statements. Read and write having similar syntax and were both blocking. So if you wanted to read something from a tape drive or a card reader, the program would stop until that I/O process was finished. And there was a good reason to stop, because your program didn't know what else to do until it got the data that it needed. And this style of programming found its way into virtually every other programming language since then. It was modeled after the black box idea, that you've got a box and it's got some process inside of it, and you've got an input and you've got an output. And so not understanding ultimately how software was going to turn out, software was developed with the same hardware model. It got stressed a little bit when we went into timesharing. In timesharing, you had a big computer which was not nearly as big as what you've got in your pocket, but it was big for its time. And it would be shared with hundreds of users. Hundreds of users on terminals would connect simultaneously to that machine and take turns in its CPU and in its memory running programs. Timesharing programs were highly modal because every read statement essentially was a mode. At the point of that read, the program was expecting one particular kind of input, and nothing else would satisfy it. So the flow of the dialogue was dictated by the program, not by the user. Timesharing depended economically on the blocking read, because when it blocked, that meant that that user was not going to be requesting any more resources. And so that was how they were able to maintain the illusion that they could have 100 people on a tiny machine at the same time. So virtually all programming languages since then have had blocking I/O. When you read, you stop. When you write, you stop. Except for C, which had no I/O at all. So with C, there was a possibility of exploring other models. Unfortunately, there was standard I/O, and that's virtually all anybody uses, so it's as though it has blocking I/O. Meanwhile, in research laboratories, people were starting to, like at SRI and like at Xerox PARC, people were starting to play with other models of organizing applications in ways that instead of having blocking read, you have other ways of interacting with the user, which provided for more flexibility, less modality. Similarly, some people who were developing text editors were finding that if they had a single read for the whole program, they could be much more flexible in the way that they served the programmer as he was editing. And also, the developers of the early computer games found that if they were trying to do something that was real-time, then blocking for user input didn't make any sense. And so the early highly interactive game systems also dispensed with the blocking read in favor of another model. It didn't get to the mainstream until 1984. And this is when most mainstream programmers for the first time were faced with this new model of programming. And it came with the Macintosh. And it was necessary in order to take full advantage of the mouse and the overlapping window display. And there was a lot of complaining from the programming community at the time that you have to write your programs inside out. Wow, it was just too hard. That we should go back to the command line. That's the way God intended us to write programs. This inside out thing just didn't make sense. It was too difficult. Some people still think so. But eventually that attitude changed. And one of the things that propelled it to change was HyperCard. Anybody remember HyperCard? The old folks all remember it. HyperCard was an application developed by Bill Atkinson, who did QuickTime or QuickDraw and Mac Paint. It initially was a version of Mac Paint that allowed for working on several pictures at once that could be in a stack, and at any moment, only the top one would be visible. Then he added to each of those planes the ability to add buttons and fields, and then to add scripts to those buttons and fields. And it eventually became a very flexible kit for developing applications. For a while, it was extremely popular. There were thousands of stacks, as they were called, moving out in the world, this new style of programming. And it was particularly effective for non-programmers. People who'd never programmed before got onto HyperCard, played with a sample program, got it really quickly, and then started writing these little things by putting code in the cards and in the buttons and in the fields. The professional programmers then saw what the beginners were doing and realized, oh, I guess it's not that hard. Apple had done some things to try to help them along. For example, they had a programming framework called Mac App, which was a template for a Macintosh application. And it had the event loop in it and the menu bar and all that stuff. And all you had to do was stick your code in there, except you had to turn it all inside out in order to be event-driven. It didn't sell. They couldn't get people to do that. But once people saw HyperCard as an exemplar, then suddenly it was, oh, this stuff's actually easy. If beginners can do it, then professionals ought to be able to do it. And then we saw a big explosion of applications for the Mac and for Windows, which had a similar model. So HyperCard was all about events. Everything was event-driven. It had functions, but they were pretty weak and weren't much used. Event handlers were the whole language. So programs were written as a collection of event handlers attached to objects, and the events would then bubble up. So if you clicked on a button, the button could handle it. If it didn't, the card would handle it. If it didn't, the stack would handle it. And these events look very similar to the events you see today in web browsers, and that's not a coincidence. So we see mouse up, key down. On card enter is now called on load, but it's the same idea. One thing that HyperCard had was on idle, so that whenever the event queue became empty, it would send on idle out. And initially there was no use for it, but people realized that they could use it to do animation. So when nothing's going on, they'll move something or replace something. They even had access to primitive drawing tools, and they could pull out the pencil and start marking pixels. And that's the wrong way to schedule animation, but it's the only tool they had, and so they used it. When the next generation of Macintoshes came out and were faster, then all of those programs worked badly because there's nothing they could sync to. And the moral of that is if you don't provide a right way, the street will find its own way. So HyperCard had a big impact on the evolution of the browser. When Netscape was developing their browser, they intended to make Netscape 2 as easy to program as HyperCard. And so they looked at HyperCard and copied its features and tried to move them into the browser. So it turns out JavaScript is very well suited to event-driven programming, and that's not by accident, it's by design. It was intended for this kind of environment. So the DOM is one of the awfulest APIs ever devised. The DOM is the API that the browser provides to JavaScript, and it is painful. When most people say they hate JavaScript, what they're really saying is they hate the DOM. They just don't understand where the border is. But a small amount of JavaScript on top of the DOM raises the level and makes it much more pleasant to use. So you can take an AJAX library such as YUI3, and put that on top of the DOM, and suddenly you've got a very good programming experience. So one of the advantages of JavaScript in this context is it does not have blocking read. It's never had it. And for a long time, this was considered as a disadvantage, and JavaScript can't read files. So therefore, JavaScript's a bad language. It's not that the language can't read, it's just that it was never given an API. But the advantage of that is that it was never given a blocking API. So when we start looking at other uses for event loops, JavaScript programmers are already conditioned to think about it correctly because they have never historically depended on blockage. So because read blocks and blocking is bad for event loops, it violates the prime directive that you never block. So JavaScript programmers are just naturally smarter about using event loops than programmers of other languages. So event loop is just one approach to concurrency. It's not even the most popular right now. The most popular would be threading, which we see in Java and most other languages. So there are always trade-offs, and so there are trade-offs with threading. The pro is a significant one, that no rethinking is necessary. You can take any existing program, put it in a thread, and it will continue to work. No modification needed, so that's a good thing. You don't have to rewrite it, make it inside out. And it's okay that programs block. In fact, that's what threads are for. Threads are there so that programs can stop. And execution will continue as long as there's any thread that's not blocked. There's some cons. One is that you have to allocate stack memory for every thread, which is not significant anymore, that memory is abundant. A bigger problem is that if two threads are using the same memory, erase may occur. And this is a bigger problem. So let's look at this a little bit. So there's often calls for adding threading to JavaScript, and this is why it's not likely ever to happen. So here we have two JavaScript programs. Each is going to run as a separate thread. And there are a number of possible outcomes of this program. Let's see, a note about JavaScript. If you store something into the element whose number is the length of the array, that will extend the array by one element. So this is how you append, is by storing to the thing's length. So we're going to append an A to the array and append a B to the array. So if each of these is in a different thread, you can't control the ordering of the threads. So two possible outcomes might be the array A, B, or the array B, A. So that's fine. That's not the kind of race I'm concerned about. This is also a possible outcome, where we just lose data. And you challenge anybody to look at that program and understand where the data go. You can be confident that both statements execute and do exactly what they think they're going to do, but in the result, data is lost. So how does that happen? I don't think so, but you could lose one. So how did this happen? So that one statement could be viewed as four statements. Okay, these four statements do the same thing. So we get the length of the array, we store something into that point. If that extends the length of the array, then the array length gets enlarged. But we've got this going on in two threads, and there's no way to control the interleaving of those statements. So one possible set of interleavings ends up like this, so that so we store one thing into the length and we store another thing into the length. We interrupt a read, modify, write cycle, so that, and then they'll both do the modify but not be aware that one guy already did it. And so this will lead to the outcome of just B. This stuff is extremely difficult to reason about, and it's really dangerous. So, and it's impossible to have application integrity when subject to race conditions. And it's difficult to see races when reading code. So this is a hazard to programming. Fortunately, we've got mutual exclusion, which allows us to lock some amount of code or some amount of memory and prevent two threads from getting at it at the same time. And there are a number of mechanisms for doing this that were popular at different times. semaphores, monitors, rendezvous, synchronization, all do the same thing but with different expressive properties. This used to be operating system stuff, but it has leaked into the applications because of networking and because of multi-core. So now it's the responsibility of applications to figure out how to make use of multiple threads. And I think that's a problem because threads are really difficult to reason about as well. So in mutual exclusion, only one thread can be executing in a critical section at a time, and all other threads waiting to execute that section are blocked. If the threads don't interact, then the programs can run at full speed, but if they do interact, then the races will occur unless mutual exclusion is employed, and that can cause a lot of blockage, and so you don't get the speed up that you were hoping for. The other problem is deadlock. So here we have Gaston and Alphonse, two threads, each is waiting for the other. And as long as they're both waiting for the other, neither will proceed, so they're both blocked. This is deadlock. This is maybe a real-world example of deadlock. We call this gridlock. This is Sao Paulo, about 2 blocks from Yahoo's offices in Brazil. It's a problem. So you've got cars waiting for other cars that can't get out of their way because they're waiting for other cars. And you can see they go off for blocks and blocks. So, so you don't want your programs doing that either. So deadlock occurs when threads are waiting on each other. Races and deadlocks are really difficult to reason about. There are people who are able to reason about them. Most people are not, and so that's difficult. These are the most difficult problems to identify, debug, and correct. They often go unobserved during testing. It may be that during testing it works fine, and it's not until you're ready to show it to your investors that the problem occurs. Or they might work while you're at small scale, and when you're ready to go to large scale, then the failures occur. It's just really, really hard. I mean, programming is all about managing sequential logic, and that's hard. Managing temporal logic is really, really hard. So getting back to our trade-offs, if threads occur, or if we're using threads on the same memory, a race may occur, which is worse than a race will occur because it's harder to detect, harder to test. There's overhead. We're subject to deadlock. Thinking is extremely difficult. We have system application confusion. In my model, threads are evil, but they're necessary evil. And when you're doing systems programming, it's one of the tools that's available to us. But they should never be employed at the application level. We need to keep those distinct. And so if a system is doing its job right, the application should never be concerned about thread safety. In my view, the biggest design error in Java was that it confused this. So Java couldn't decide if it wanted to be a systems language or an application language. So it tried to be both, and by doing so, it forced threads on the application programmer, which I think was unfortunate. Fortunately, there is a model that completely avoids all of the reliability hazards of threads, and that's our friend, the event loop. So let's look at the pros and cons for event loops. We're free of races and deadlock, which is a good thing. There's only one stack, which we're constantly reusing on every turn. That saves memory, but that's not a big deal since memory is so cheap now. There's very low overhead because we're not doing a lot of blocking or process switching, things that are slow. We're just doing computation, pulling things off the stack and executing them until they finish. And it's resilient. If a turn fails, the program can still go on. We just wait for the next event and on we go. Whereas if a thread fails, there's an exception and it pops up and it's gone. It's possible that critical state was lost in that exception process. And if there are other threads that were waiting on that thread, then they may be blocked forever, and so you can have cascading failures. Now there are cons. The first is you got the prime directive, so programs must never block. And programs have to be written inside out, but we can deal with that. And turns must finish quickly. If you have a turn that cannot finish quickly, it cannot run in an event loop. And that is a problem, so let's look at that. So we have two solutions for long-running programs. One is a technique called iteration, in which a long-running task breaks itself into a sequence of turns. For example, you might have a function which represents one major iteration When it's finished, it does a timer event to call itself in no time, and then it can return. That turn is finished, and then later it gets to run again, and it can keep doing that until it completes. And the time it takes to complete could be extremely long, but any turn is going to be bounded. It's going to be not too long, and that allows the rest of the event loop to continue running. So we can have long-running jobs, but not tie up the main loop. The other thing we can do is simply move that task into a separate process. And this is the worker idea that, that Google's been doing, which I think is brilliant. That there are just some programs which should not be in the main event loop. So if we're factoring very large numbers or something of that sort, that shouldn't go on there, but anything else can, or be turned into a series of callbacks. So I want to stop just for a minute and talk about the remote procedure call. This combines two great ideas, functions and networking, and produces a really bad idea. Essentially takes network I/O and turns it into blocking read. Because when you do this, the network takes a lot more time generally than the file system. So the program literally blacks out. It can be gone for some period of time and has no awareness of its having blocked out. And in reading the program, it is by design difficult to see where this can occur. This can result in a terrible experience for the user because lost time equals annoying delays. And it's difficult for us in analyzing the code to see where this lost time is going to occur. So keeping the user waiting without warning is disrespectful and rude, and we don't want to do that. And remote procedure call makes it extremely difficult to treat the user well. So instead what we want to be doing is latency compensation. So at a minimum, we want to acknowledge the user's input immediately. So they clicked or they typed or did something. We may not know yet what the consequence of that is, but we know that we did it, and so we can offer that feedback immediately and then and give them further feedback later. We don't want to lock up the interaction while waiting for a server's response. In some applications, it's reasonable to predict the server's response and display that immediately, and then later display a correction if that prediction turned out to be false. For example, in a chat application, the user types something, and that will be sent to the server and then found out to all the users. We can display that to the user immediately so that they can see that it was typed, predicting that the server is probably going to echo it back to them anyway. If the server rejects it, then we can put that message up instead. But it allows the user to get feedback earlier. They feel better about the interaction. Life goes on. So in the threaded environment, security is really difficult to reason about because we don't have consistency. And without consistency, there's no security. Now, in an event loop-driven model, I think security is much easier to reason about, but simply being in that model doesn't guarantee you're going to be secure. And the browser is itself a very good illustration of this. We have something that we call the XSS, the misnamed cross-site scripting attack. This is the biggest security vulnerability that we have in web browsers. It's misnamed, and the name is a problem in a couple of ways. The first is that there are some versions of this exploit which do not depend on a second site or doing stuff across sites. It can all happen within one site with one user. So the name does not really tell us about what the problem actually is. Also, it turns out cross-site scripting is not a bad thing. It's a highly desirable thing. We call it mashups now. It's a way of taking programs that represent multiple interests and to have them all run together cooperatively for the benefit of the user. That's something that we want. It's not a problem. It's a goal. And so having this security exploit carrying that name is at best a distraction. So the XSS attack has two fundamental causes. The first is the sharing of the global object. JavaScript doesn't have a linker, but it can have lots of pieces of script running on the page. So the way the browser deals with this is it throws all of those scripts into a common global space. And so the way the components link together is they simply share global variables. And that's a problem to the extent that global variables are evil. In JavaScript, they're unavoidable, they're necessary. And so anybody who can get to the global object, to the global variables, has access to everything that's in the context. So they've got access to the DOM, they've got access to the network, they've got access to all the other components. There's virtually no security. The other is the misinterpretation of HTML. Turns out HTML is a surprisingly complicated language, and it has other complicated languages embedded inside of it, including URLs, CSS, and JavaScript. Any of those can be nested inside of any of the others. You can even put JavaScript in a URL, put that URL in CSS, put that CSS in a script, put that in HTML, put that in another URL. And each of these languages has different encoding conventions, commenting conventions, escapement quoting conventions. Statically analyzing a piece of code and deciding if it is safe to put into a JavaScript context is extremely difficult and is often done incorrectly. And so these two things together allows a third party to inject code onto a page, and that code then runs with all the privileges that the originator's code runs with. So what happens if an attacker can get some script onto your page? What can he do? First, he can request additional scripts from any server in the world. The browser has a security policy called the same origin policy, which limits your ability to interact with other sites. But this is wide open. So if you can get a little bit of script onto your page, you can then go to the evilest server in the world and get as much additional script as you want. The browser does not interfere with that at all. The attacker can read the document. The attacker can see everything that the user can see. It can also see a lot of things that the user cannot see. For example, he can see all the comments, he can see the hidden fields, he can get the cookies, he can get everything that was sent from your server. The attacker can make requests of your server, and your server cannot detect that the requests did not originate with your scripts. If you require additional tokens of authentication in order to frustrate cross-site request forgery problems, which you should, that doesn't help because the attacker has access to those tokens and he can send them himself. If you're using SSL, and you should, the attacker gets access to your secure connections. If your server accepts SQL queries, then the attacker gets access to your database. Now, if instead you are concatenating SQL queries using information obtained from the browser, then you probably are probably giving access. And it's because SQL was optimized for SQL injection attacks. It is not a safe language. The attacker has control over the display and can request additional information from the user. And the user cannot detect that the request did not originate from your server. Now, most of the browsers now have anti-phishing Chrome to help the users discover if the page they're talking to is legitimate or not. Problem with that is that most users don't pay any attention to that. But if they did, in this case, it will tell them it's A-OK, go ahead and give up the information. And that's because they are looking for where the HTML came from and not where the script came from. So if the HTML came from your server, it's okay. They can say that it came from you. They can say that it matches your certificate. It's all right. Now, on some sites, anytime the user tries to do something scary, they'll ask for a password on the assumption that the attacker doesn't have access to the password, and that way we can be sure that this is legit. But the user has control of the display, or the attacker has control of the display, so the attacker can ask the user, what's your password? And there's no reason why the user shouldn't give it up. If your site routinely and unexpectedly asks the user for their password over and over again, what you're doing is training the user to give up the password the next time the attacker asks for it. The attacker can then send this information to servers anywhere in the world. Again, the browsers have the same origin policy. Again, the same origin policy does not restrict the attacker's ability to send this to the evilest site that there is. Anybody alarmed? Uncomfortable? You'd be surprised how easy it is. For example, how do you get some JavaScript onto an arbitrary site? Say I want to steal the cookies from your site. So I give the user who I want to trick a URL, and they click on it, and they'll go to your site. Okay, that's easy to do, right? That URL contains your domain name / script, some evil stuff, close script. Now, you don't have a file called that on your site, so you get a 404 page. And by default, the 404 page that your server produces simply takes that file name, concatenates it into the middle of an HTML stream. But now, instead of being a file name, it's an executable. And when the user sees it, it is now in your domain, okay? So they can load additional scripts now, and everything's going to say it's yours. And they can transform the screen in any way they want. It's really easy. It's kind of disgusting how easy it is. And the number of ways that people have found to do it is vast. The corpus of XSS exploits that are known for browsers is vast. It's so big that there's no way that you can expect developers to be aware of all of those exploits. It's just too much for anybody to know. And it's constantly growing. People are finding new exploits all the time. And we've got lots of new versions of browsers coming online now, and all the HTML5 stuff. And so the space in which new exploits can be inserted is growing even faster. So the consequences of an attack are horrible. There can be harm to customers, loss of trust. There can be legal liabilities for leaking user data. There's talk about criminal liability for exposing critical information. And the browser does not prevent any of these things. Web standards require these weaknesses. Now, there are bugs in the browsers, and bugs certainly lead to security problems. I'm not talking about bugs. I'm talking about standard behavior, that if your browser does not expose you and your users to this specific harm, it is not standards compliant. That is the state of web standards. The standards are broken and in bad need of repair. This has been going on for 15 years. The XSS attacks were enabled 15 years ago next month. And we have made no progress since then on correcting this mistake. And tragically, the HTML5 effort ignores this problem and worsens this problem. This is a quote from the editor of that standard, where he denies that they have any responsibility for it. So it actually makes things worse 3 ways. First, HTML5 is really complicated, and complexity aids the enemy. So there are lots of new places now. The attack surface is much larger, many new opportunities for hiding bad stuff. Second, the attacker now gets powerful new capabilities he didn't have before. He's got a WebSocket API, which is going to allow him to connect more easily to lots of other servers to get behind firewalls and go places where he couldn't go before. He's got local storage. He's got a local database that he now has unrestricted access to. He can do anything he wants. He can steal that data. He can poison that data. He can inject stuff which will make it easier for him to come back in the future. All of that is available to him. There is nothing in HTML5 that frustrates any of that. And then third, HTML5 itself is huge, and it's going to take years to reach completion. We're seeing some of its features coming online now, but it's not going to be finished for a long time. And so if that's the case, it is forestalling the solution to this problem, which I think is more important than any of the other features that HTML5 provides. So the browser is a loaded gun pointed at your head, and this is the trigger. This is an element from a template language like PHP or ASP. That it is easier to insert raw text into an outgoing HTML stream than it is to encode it properly to make sure that it will not do bad things. And so that's how it's all too often done. So page templates are maybe a third cause of this. But they're not a necessary cause, but they're popular. So a page template system like PHP, ASP, or JSP, all of these Ps, are not a good match for the way that we build modern websites. They made sense 15 years ago when PHP was created, but today a page isn't a page really. It's an amalgam of widgets, and they are very complicated structures. And a template is just the wrong framework for constructing these things. And it's much too easy to insert text into a context where it is misinterpreted and executed, completing an XSS attack. So can we do better by using JavaScript on the server? And there's some obvious advantages. One is that we can take our understanding of JavaScript and apply it to this other domain. So it turns out server-side JavaScript is not a new idea. Netscape offered a server-side JavaScript product in 1996, but it was awful. It looked like PHP, except it was JavaScript. It had all the disadvantages of a page template system and no compensating advantages. So fortunately, it failed. So we have none of that legacy to constrain us now as we think about how would you do this right. So what if we had server-side JavaScript with an event loop? Because that's a better way to do these sorts of programs. And yeah, we can do that. One of the leading examples of this is Node.js. Node.js implements a high-performance web server in a JavaScript event loop that runs on Google's V8 JavaScript engine. It is a high-performance event pump. And it has a read statement which has a callback, which to my eye is the right way to do read. So it got that right. In fact, all of the calls in the Node.js API are non-blocking, with the exception of a couple of synchronous functions and a require function, which is used for loading programs. I'm hoping eventually to get this repaired, because one thing we've learned on the web is if we give people the tools for doing things the wrong way, they will certainly do it the wrong way. And I don't want to give people opportunities for doing blocking inside the main server event loop. So the obvious advantage is you can now run your code on both sides of the network. At Yahoo, we have an AJAX library called YUI3, which we have now running on a server on V8. And it has a pseudo DOM in it, which has the same API as the browser's DOM. So we can literally have programs running on either side. And we find some really nice advantage of this. One is there are some applications in which we have a very large amount of code, such as mail. The way we would want to do those applications in the main AJAX style is we would send all of our code over to the browser, let it run there, and it would generate the page on the client side. The problem with that is that the networks are so slow and the programs are so large that we introduce a lot of latency, and it can take some time before the user finally gets to see an image. So an alternative to that is generate the first page view on the server side, send that over as HTML, and then send the scripts over so that the user's got something to look at while we're waiting for the pages to get loaded. And this actually takes a little bit longer, but the user's experience is that it's much, much faster, and so that's a really good trade-off. And it used to be that we had to write the server-side generation in PHP. So essentially we had to write the program twice. Now we only have to write it once. We can have exactly the same code running in both places. We can also deal with deficient browsers. So if there's a browser that's not smart enough to do the full AJAX thing, it doesn't run JavaScript properly, it's got an inadequate DOM, we can just say, fine, all you get is page views from this. We'll do it the old way, the Web 1.0 way. And so we can just have the server generating HTML streams to send back, and that's all it does. And there are hybrids of that. We can also have web services, which can return, based on the parameters that they're given, either JSON data or an HTML widget or a complete page. We've got those options. Again, it's one piece of code that can do all of those things. We're also finding more and more that we've got pages that are assembled out of lots of components that come from lots of different servers and services. And in a template system, the way you do that is you go serially from one to another, asking for something, getting its data back, and so on, blocking on each one. And so the latency you pay is the sum of all of those requests. Whereas in JavaScript on an event-driven system, we can make all those requests at once and then wait for them all to come back. But we don't actually wait because they all come back as callbacks. When all the callbacks are satisfied, then we can continue running. So we end up paying only for the largest latency, not for the sum of the latencies. So huge improvements there as well. So we've got new patterns of programming now that we didn't have in the browser, where we've got callbacks inside of callbacks inside of callbacks, as we have dependency on other things that could be happening. And we've had people trying to write it in that way and discovering that their code gets really complicated and they're injecting a lot of dependencies which are unnatural and awful looking. So we're experimenting now with new patterns. For example, a requester function which will encapsulate a request and its callback, and it will take another function which it will then call on completion of the callback. And having a requester function of this sort, we now have something that's composable. So for example, I could have an array of those and pass it to another function which will call them all in parallel and then organize and synchronize the results, and can also handle a timeout as well. If any of those is taking too long, it can bail. Similarly, we can set up a set and do them sequentially. So I'm not convinced that this will be the best form. We're seeing lots of really interesting experiments in functional programming and interesting compositions of how to deal with these different threads, not threads, but flows of goodness. And we'll see how that turns out. I was talking to a friend of mine recently about what we should be doing next in JavaScript. There's a lot of pressure on the language to push it in different directions, but now that it's become the world's most popular language, we're very constrained in how much we can push it. If you have a failed language, it's much easier to radically change it, but if it's popular, you can't change it without breaking it, and so we're very sensitive to that. And everybody wants this language to be more like a different language. Like, there are a lot of people who want it to be more like Python or more like Java or a language that they like. I'd like it to be a bit more like Scheme, so that tail recursion thing we were talking about earlier, I'd like to get that into this language. As explained to my friend, some of the advantages that you get from it, like you can do continuation passing style, in which you've got functions that never return, that they just keep going forward, and you pass to them the function to call with the result, and that function keeps going, and you can go. And amazing patterns of program construction, but it cannot work unless you've got tail recursion. And his answer was, well, I've never used continuation passing style, so I don't see the value of it, which I immediately recognized as being a stupid answer. And the reason I knew it was a stupid answer is because I have used that same answer myself lots of times, and I've been hearing it my whole career. I've heard it used to justify things for, we don't need recursion, we don't need closure, we don't need garbage collection. I read a white paper recently that was comparing two application systems, one written in Java and one in C++, and they were doing a checklist comparing feature by feature. And they got to garbage collection, and they said that garbage collection is a programming convenience. And so they measured the number of lines of code in their C++ framework that were explicitly releasing memory. And they determined that it was a very small number in respect to the body of code, and therefore concluded that garbage collection is just not important, which completely misunderstood, misrepresented what garbage collection is. It's not a programmer convenience. It's a reliability mechanism. It's a way of assuring yourself that you're not going to get dangling pointer errors. It's a way of considering algorithms which are just too dangerous to contemplate unless you've got automatic memory management. And that's the benefit of garbage collection. But they didn't understand that. So basically their conclusion was that if you're a C++ programmer, you do not need to understand Java, you don't need to understand garbage collection, and you can feel good about that. And that's a problem. You know, it's sort of the history of our profession, that the guys who should know better don't. So when Grace established the discipline of software engineering, she confronted this stuff. And we have come a long way since she got us started. But I feel that we should be a lot farther along by now than we are. And it's because we keep getting in our own way that we find our lack of understanding to be comforting rather than problematic. And so generally the way we make progress in software is by waiting for one generation to die off so that we can get critical mass on the next set of new ideas. And I think that's what we've been doing all along. One final thing. Usually if I'm talking to an audience of web developers, this is where they burst into spontaneous applause. Now it turns out, so IE6 is the source of most of the pain and misery for web developers. But IE was once, and for many years was, the best web browser the world had ever seen. When it first came out, I think it was in 2000, there was nothing better. Now, it turns out Netscape set the bar very low. So it wasn't hard for them to be the best web browser in the world, but they were. And the reason the Ajax revolution in 2005 was successful was because of the goodness that was in IE6. Now, in 2000, when Netscape self-destructed, Forrester said that the web is over. So Microsoft said, oh, that's good. You know, they didn't buy the web in the first place. So they disbanded the IE team, had them go to work on Avalon and other new things to do the next thing that was going to happen after the web. And they were blindsided when Ajax happened and it turned out, oh, the web's not dead, so they need to get going again. So one of the difficulties in going forward is that this thing's 10 years old now. And we've got newer browsers which are new. And they have lots of functionality which this one didn't have. But web developers are expected to make their applications work as well, and in some cases identically, with this one. And it's really, really hard. I mean, Turing says, yeah, you ought to be able to do that. But practically, it's really, really hard. And so there's a lot of good reasons to say this thing must die. Also, we're making improvements to JavaScript, to ECMAScript. We're making it a better language. But that doesn't help if you're programming in IE6, because it's stuck in a 10-year-old language. It cannot be upgraded. So ultimately, in order to go forward, we have to somehow get rid of all copies of IE6, or at least pretend that they're not there and fail to work the same way for them. Then there's IE7. IE7 is more modern, is better, but is still deficient in a lot of ways, and everybody wants to go away. Even Microsoft would like to see it go away. Then there's IE8, yeah, same story. I mean, different number, but it's the same tune. Then finally, there's IE9, and I haven't made my mind up about this one yet. Microsoft has done some really good work on IE9. And some of the previews we've seen are quite impressive. And there's a possibility that it might be, for a time, the best web browser in the world. There's one problem, and that is ECMAScript 5. ECMAScript 5 is the latest version of the ECMAScript standard. That's the name of the standard for Java. You can ask me later why they have two names, but it is. And ECMAScript 5 attempts to repair some of the security problems that are in the language, and that's of a huge benefit to all of us. But a difficulty with security is that you can't add security, you have to remove insecurity. So in a programming language, it means that there are some things that people used to be able to do that we want them not to be able to do anymore. But the problem with the errors that are in JavaScript isn't that they're useless, it's that they're dangerous. That people have found uses for every mistake that's in the language, and there are a lot of them. So we can't just correct them without breaking the web, and we don't want to break the web. In fact, it's hard not to break the web making any change at all. So we've added a strict mode to ES5 so that you can now opt into this stronger, more regular, more natural language, and that's good. And it turns out that we can make mashup frameworks that allow code from mutually suspicious third parties and allow them to run together without being able to compromise each other. So we have a solution to the mashup problem that happens because we've got ES5 strict. Microsoft, in their previews, has shipped large parts of ES5, which is wonderful, but they have intentionally excluded the strict mode. So the best, most important feature of ES5 is not there. And I've asked them, are you going to have it before you go final? And they say they can't answer. And I don't know if that's because, well, Microsoft has a long, confusing history, and they have to be very careful what they say in public. So maybe they're going to do it, and maybe it turns out okay. Maybe they're going to ship the complete language, and it'll be great. And it may be, again, the best web browser in the world. Or maybe it just is the next number to go on the list of versions of IE that we have to get rid of. I don't know. But on that, I say thank you and good night. Yes.
So a comment and a question. Actually, the comment is I think JavaScript is a great language. It's very simple, elegant, powerful, has a very high ratio of power to complexity, which is, for me, what defines goodness in computer systems. So the question is, it sounded like you were suggesting that running JavaScript on the server would solve the XSS problem, but I didn't see how that came out in your slides. Are you making that claim, and if so, how?
Running JavaScript in the server on YUI, I think it does. And the reason it does is we don't use templating for generating HTML streams anymore. We do it programmatically. So YUI contains widget libraries which will construct HTML structures for you. And then we can, with our pseudo-DOM, serialize those structures so that we're guaranteed that they're properly encoded, and then send those to the browser.
My experience is that templates, for all their evils, are an exceptionally simple and concise way of generating HTML, and that the DOM-like models tend to be very tedious and verbose in comparison. And so there's a natural tendency that people want to use whatever's simplest and easiest.
Right, and that's why YUI is so important, because it is actually simpler than the template model. For the widgets that it can make very complicated widgets programmatically with much less effort than trying to build equivalent HTML structures. So if it were just raw JavaScript on top of a pseudo-DOM in a server, I would agree with you. But having a good AJAX library in between, I think makes a big difference. Yes?
Can we play with YUI?
Yeah, YUI has been available to the public for years. So you can go to developer.yahoo.com, and there's a lot of YUI there. Some people are calling it UI now, so we may end up changing the pronunciation. But there's lots of documentation, lots of examples. It's free for everybody. If you decide to adopt it, you can even load it from our distribution servers, so you don't even have to pay the download charges. Anyone else? Yes?
Yeah. So JavaScript's turned out to be a much more interesting and powerful language than anyone expected. In particular, we were showing examples where functions were passed that were given parameters, callbacks, which were then used later to inform in the event loop. Was that design intentional, or was it something that came because of the abstractions that they happened to choose, or what? What underlies the power in the design?
Yeah, it was intentional. So Brendan Eich is the creator of JavaScript, brilliant man. He was working at Silicon Graphics doing operating systems. He interviewed at Netscape when they were looking for someone to do the HyperCard thing. And they asked him about scripting languages or languages in general. He told them that he was a language jock, that he was getting ready to write a Scheme interpreter, and he thought Scheme was really powerful and might be a good language for their application. So they said, oh, great, this guy's really smart, so they hired him. Just before he started work there, somebody at Netscape found out what Scheme was. And the first day at work, they said, no, you can't do that. You can't do Scheme. You got to do a language people like. So make it look like Visual Basic or Java, something that's going to be popular. This is for beginners. We can't have all the parentheses. So don't do Scheme. You can't do Scheme. Do something simple. So he then took Java syntax and started noodling with it and took some other ideas. In about 2 weeks, he made a programming language from scratch. Just amazing. And he put Scheme in it, and he didn't tell anybody. He didn't tell anybody at Netscape that it had lambdas in it. And so none of the documentation that came out from Netscape or from anybody else mentioned this most amazing aspect of the language. We didn't discover it until years later. And it's not in there by accident. It was in there intentionally. And that is what makes it such a wonderful language. That functions are just great things, and you can compose them. And because they're first class, you can have a function that receives a function as a parameter and returns a function as a result, which will call that function in the future. And you can just have these amazing patterns of composition that you can't do in any other kind of language. And it happens in JavaScript. And the Ajax revolution succeeded, I think, because of the power in JavaScript. If JavaScript had been the crappy language that everybody thought it was, Ajax would have failed. So some serendipity there, that it was a better language than we deserved. In fact, given the process that creates web standards, we deserve something far, far worse. Because nobody was paying attention. I mean, nobody at Netscape knew that he was doing this. So there was no review, no study, no testing. It was just slap it together and...
It was called LiveScript to begin with?
Its working title was Mocha, and then they released it as LiveScript. Sun and Netscape decided that they needed to align together in order to defeat Microsoft. Because if they went independently, then Microsoft would play them off against each other and they'd both fail. But the big point of contention was... that's a later story. The big point of contention was what to do with LiveScript. Sun thought it was simple, you just kill it. And Netscape said, well, no, for two reasons. One is they still believed in the simple scripting idea. And most beginners cannot write hello world in Java. So they wanted an easier language. Also, they were in a race to get this thing finished and to get Java integrated into it. And they had JavaScript, or LiveScript at the time, working with their DOM, but there was no connection for Java in the DOM. So they quickly put in a connection between Java and JavaScript, and they called that Live Connect. But without Live Connect, there was no way for the applet to interact with the rest of the page. And so they were forced to do it. Mark Andreessen, maybe as a joke, suggested, let's call it JavaScript. And that way they wouldn't hate it so much. And Sun accepted that on the condition that Sun owned the trademark. And Netscape agreed, assuming that Netscape would get a license to use the trademark, and that's what it was. Then Microsoft knocked it off, and they couldn't get a license to use the trademark, so they called theirs JScript. So then Netscape went to try to get a standard. They first went to W3C. W3C said go to hell, so then they went to ISO, and that didn't work. And then eventually they went to the European Computer Manufacturers Association, or ECMA, which is a long way to go for a California software company. But they thought that's where they could get a standard. But Netscape put a condition on the standard saying that you can't call it JavaScript because we've got the exclusive right to call it JavaScript. At that point, ECMA should have told them to go to hell. But instead, they went ahead and produced a standard. And the committee, in addition to designing the language, also had to come up with a name for it. And they came up with things like WebScript and NetScript, but they couldn't agree. So they published it with the working title, which was ECMAScript, which is maybe the worst name put on a programming language. Yes?
So I found that sometimes when someone talks about whether they like or dislike a language or hate a language besides hating what they don't understand, you find that, say, with Objective-C, they don't hate Objective-C, they hate the frameworks that come with it because they're too big, too complex, too difficult. I wonder if JavaScript has a similar problem, not that the framework is too complex, but there's too complex a set of frameworks, which makes it hard for a programmer to join a project that uses a different framework, or hard to compose software that comes from different sources.
That's a really good point. So we have a situation with JavaScript in the browser where the DOM is an awful API. But fortunately, JavaScript is so expressive and powerful that a small amount of JavaScript can fix it. And so we have fixed it. And we've got maybe hundreds of Ajax libraries that fix it that are all mutually incompatible. So we've created another problem. Now that we're moving to the server side, we're trying not to make the same mistake. So everybody has settled on Node.js. That's only one possible server-side implementation. but it looks good, and so we're all saying, yeah, let's try to all go with this one. And instead of trying to port all the Ajax libraries to it, we're looking at, maybe just YUI by itself will be enough. So we'll see how that goes. Yes?
I've been doing Node.js recently, and so I've run into the same problem, which is like a lot of nested callbacks, especially when you have a database that is asynchronous and it's also like a NoSQL database where you have to get key values, and then you just have like a lot of nested callbacks. So I was wondering if you could talk a bit more on solutions, because I've tried a bunch of different things, so like jQuery chaining and possibly even like looked at stuff like monads, and that seems like a nice thing to solve some problem like that.
Yeah, and I can't tell you what the solution is going to be yet, but I'm sure it's going to be something along those lines. We're going to find some structure which is composable, which doesn't get terribly complex, which has the right sort of module boundaries, all that stuff that we look for in good software engineering. I'm confident that exists within the JavaScript language. We just haven't decided what it's going to be yet.
So you're saying like without any extensions or future version of JavaScript?
I don't think we need to change the language at all. I think most of it can be encapsulated into a new library, and the rest of it is just good practice. And so I think we're maybe a few months away from that. I think it's pretty close. Yeah?
Can you recommend a starting place for learning to use JavaScript well?
You already know how to program, right?
Yeah.
Yeah, so it turns out I wrote a book, JavaScript, The Good Parts. As you'd expect, it's a very skinny book. But that'll get you started. It's not a book for beginners. It assumes you already know something about what you're doing. And
Pointers to your lectures in this general serial, also on the
that's
website.
true, yeah. I've got tons of crappy lectures online. You're welcome to look at all of that stuff for free as well. Yes?
Could you say some more about server-side JavaScript and security issues? Can I tone down the browser-side stuff to get rid of some of these problems?
I'm sorry, can you do what?
Restrict the browser side in some way to maybe avoid some security issues.
You can, but the hazards still exist in the browser. So I'm hopeful that we can create some new web standards that repair the browser. I think there's actually an easy solution to the XSS problem. It'll just require the will to get it standardized and implemented. But the implementation should be trivial. I think the standard itself would be trivial, but we need to get it done. And we've not been able to do that because of the HTML5 distraction. Yeah.
There's the other thing from Scheme that leaked into JavaScript, and that is read that reads something useful, namely tables, lists, more complex data structures. Now, it doesn't read enough, but it reads something more than just a character and lets you deal with it. So, eventually, people will get over the aversion and will end up back at Lisp. Where we had read, we had programs that could write programs, all this stuff. Garbage collection was impossible. Common Lisp was too big. It's just now smaller than everything else. Common Lisp, the original bloated language.
Right, and everything eventually wants to be Lisp. So it could be that that's where JavaScript goes. One view of JavaScript is that it's Lisp with C syntax, and that's not very wrong. So it could be that's where it wants to grow. Yeah.
You're very enthusiastic about the event-driven programming model. There's a lot to be said for it, but you do get into some major problems. One of them is that whoever controls the receipt of events rules the world. And that's usually some framework. And it's only one framework. You're stuck with, if you have libraries, which are called, you can have multiple libraries in the same program. But it's very difficult to have more than one framework. So whether you are called or whether you do the calling exerts a very strong level of control over how things are done. And this is why there seem to be so many frameworks. They don't mix.
No, I disagree with that. In the browser, there is one event loop, and it's owned by the browser itself. And any framework can hook into that. But they can work together cooperatively if they want to. But ultimately, there's not really a need for multiple frameworks. It's more a historical accident.
There's one true framework?
One true event.
Yeah, there's one true event loop, and then the rest is left to the reader.
But but it's great that I can't have inconsistency, but it also means that I paid for 4 processors and only one is working on my page.
Well, not necessarily. So
Unless they're separated into separate processes, et cetera.
well, you could do that, or you can also have more specializations. You could have one thread which is managing the disk I/O and the network I/O. All the blocking stuff goes into that thread. And you could have another that is doing workers and so on.
But in my browser for my page, I'm pretty much stuck with one. I mean, I can have one per process, but the page is essentially a process.
That's true. So another option that we're coming up with is that there's very poor modularity within a page. So everything is all in one tree and nothing's protected or isolated from anything else. So we've had experiments in the browsers where we've seen each tab be in a separate process, which is looking to be a very smart thing. We can then take that further and say we've got modules within each page, and each of those could be a separate process. And we have asynchronous JSON messaging between those. And that looks like a very fruitful direction to go in. Yes.
So what browser do you use?
I'm using Chrome. I'm using Chrome for all my daily stuff. Depending on how it turns out, I might switch to IE9. We'll have to see about that.
Chrome seems to be pretty good. Firefox still remains, I think, pretty much the standard, at least in the space I visit.
It depends on what community you're looking at. If you're talking about the world, IE is still by far the biggest brand. Firefox is a distant second. And then the other 3 are vanishingly small. That there are many more people on obsolete versions of IE than all the minority browsers combined. So another reason for why we need to get rid of those. Yes?
So there are a ton of tools out there, well, depending on how esoteric you get, that will pre-process your JavaScript files, which are not technically JavaScript, and then spit out some JavaScript from there.
Isn't that amazing?
So I work along with some other people's project called ParentScript, which basically will satisfy some of the Lisp gurus because it takes S expressions and churns out some gnarled-looking JavaScript, but it gives you Lisp-style macros. Other cool things that you get in Lisp in the browser. So I was wondering if you have any officially sanctioned preprocessors or language additions.
I don't. I'm recommending that people learn JavaScript. That it actually is, if you avoid the bad parts, and there are a lot of bad parts to avoid, but if you stick with the good parts, the scheme and self pieces, it's a really good language, and it's worth your time to learn it. But you certainly have the option of doing the other thing as well, and it's amazing that JavaScript has become the virtual machine of the net. We thought that the JVM was going to be that, but it's JavaScript. I mean, Google is translating Java into JavaScript so that they can run it everywhere. And we're seeing new languages like the parent thing and CoffeeScript and others that are being designed specifically to compile into JavaScript for execution. Amazing stuff.
And that is pretty much the end of the tape. So, bonus time.
For more, please visit us at stanford.edu.